All right, let's take a minute to walk through Kepler's three laws using this really slick planetary orbit simulator. Now, if you see, I can actually set up this simulator for any planet orbiting the sun. I can set it in motion. I just start the animation, and here's a planet orbiting around the sun. In particular, this one is set for Mercury, but I could set it for any planet in our solar system. So here's the Earth. This is approximately what its orbit looks like. And here's Jupiter. You can see. Now, ultimately, when I change these settings, all I'm changing are two variables in the planet's orbit. One is its semi-major axis, which is our measure for how far away is this planet from the sun. The other is its eccentricity, or eccentricity. I usually say eccentricity, and that's kind of a measure of how oval-like is this orbit. So if a really high eccentricity, which is like approaching 1, it gets more and more like an oval, and an eccentricity of 0 means you're basically a perfect circle. Now, what Kepler's first law was, and really we can attribute Kepler with this huge realization, which is that all orbits in a gravitational environment, all orbits are ellipses. The planet moves in an ellipse or an oval. And an ellipse is a very specific mathematical shape. There's equations which describe it. We won't get into the equations too much. But what Kepler's first law is telling us where the sun is located in response to this overall shape. So what defines a ellipse as a mathematical shape is that an ellipse has what are called focuses or foci, two foci. Now, if you think about a circle is really defined by its center point and its radius. Okay, so I can show those two things more or less like this. A circle would be a center, which is where the sun is, and a radius. Here, maybe this is a better way to show it there. Semi-major axis. Well, an ellipse is defined by not one center, but instead two foci and a semi-major axis here, which is the distance from the object doing the orbiting to the exact middle point of the ellipse. So what Kepler's first law is that the sun is always located at one of the two foci of the planet's orbit. So planets orbit in an ellipse, and the sun is located at one of the foci. The other one is empty, just empty spot in space. There's really nothing special about that spot in space. So that would be how we can see Kepler's first law. The sun is at one of the focuses. Now, Kepler's second law is really kind of an interesting one, and what it has to do with is, here, I'll get rid of that empty ellipse. There we go. What Kepler's second law tells us is something about how fast a planet moves in its orbit. So again, if I have a planet that's orbiting in a perfect circle, which can happen, if I have a planet orbiting in a perfect circle, that planet is going to orbit at a constant speed all the way around in the circle. And but Kepler's second law tells us that for planets orbiting in an ellipse, it travels more slowly when it's farther away from the star. Oh, you see that? It's sped up. So when the planet is far away, it's going slower. And when it's closer, it's going faster. And it's doing so in a very specific way. And so Kepler's second law is often described in terms of the area swept out by a planet. So I could do this kind of cool sweeping. So when the planet is close to the star, I can sweep out an area, there's an area over a certain interval of time, right? And when the planet is very far away, that same interval of time will produce an area with this that is the same. So equal areas. Now, you'll notice it looks like a much thinner triangle, right? But the area of these two triangles is the same. In fact, any area that I sweep out, right, as long as I'm using the same interval of time, will have the same area in it, inside that triangle. So that's why we say this Kepler's second law is ultimately that a planet will sweep out the equal area in equal time, regardless of where it is in its orbit. Isn't that kind of interesting? So I can just set it sweeping continuously. I think that's kind of an interesting way to see it. No matter where it is in its orbit, it'll be sweeping out equal area. And in practice, what that means is that planets move faster when they're closer to the star they're orbiting. Okay, now Kepler's third law, let's take a look at that. Kepler's third law is really an equation that relates the total time it takes a planet to go around the star as that relates to the distance from that star to the planet. So we can see this really clearly if I go to Mercury. Okay, so here's Mercury, and you can see how fast it's going around because the semi-major axis of Mercury is 0.3 AU, right? So it's a very, I can show it here, the semi-major axis. Okay, it's like half an AU, let's say, half the distance between the Earth and the Sun. Now, if I can see how fast Mercury is going, if I compare that to Jupiter, let's say, whoa. Now look at this. This is the same time scale, right? This is the same time scales we saw before, but now the distance from Jupiter to the Sun is 5 AU, right? So this is like 10 times further away than Mercury was. And you see it's going quite a bit slower. So Kepler's third law tells us how the orbital period relates to the semi-major axis. In other words, how the speed that the planet's going around relates to its overall distance, its average distance, sort of from the star. And it relates with this really specific equation, which you can see here. And you're actually going to do some problems involving this equation. So I just want to kind of show you how you can do some math with these problems. So the equation is right here, and you'll see this equation on our equation sheet as well. It's p squared equals a cubed. P squared equals a cubed. And so we can actually, let's like just do a quick problem or two so I can show you how this works. And we can do that in the case of Jupiter, right? Because if I know the semi-major axis, that's A right here. So if I know, for example, that the semi-major axis of Jupiter is 5.2 AU, right? Then I can find what its orbital period is in years. And the way I'm going to do that is by using this equation. So the equation is that p squared equals a cubed. Now, this is maybe something you haven't figured out how to solve before, but if you wanted to solve for p, all you would have to do is you have to undo this squared, right? So you would take the square root of this side and the square root of this side. So we could say that the period, and this will always be true, you could always have this equation, you could write this right on your equation sheet if you want to. If you have a problem where you're trying to solve for the period in Kepler's third law, it's this. The period is just the square root of the semi-major axis cubed. So I can use a calculator and figure this out. If I were to plug in 5.2 to the power of 3, I get something like 140.6. And then again, I can use my calculator to take the square root of that. I'm doing that right here, actually. Second square root. And it tells me that the orbital period then would be 11.8 years. Now, if you were paying attention, you maybe saw that right down here, 11.9. Okay, so it's actually 11.85. So you could round up to 11.9. So you can solve this for yourself. So if you know how long it takes a planet to go around, you can solve for A, or if you know A, you can find P. You can go either way. In fact, let's just look at an example going the other way. So let me just try to erase this really quick. And let's look at another example of using Kepler's third law. Now this is really powerful, by the way. Kepler arrived at these equations just by using a mathematical description of ellipses, which is like a really simple shape. Now, it's not as perfect of a shape as a circle, but it's still mathematically a very simple shape. So let's do another example. This time, let's pick a different planet. How about? How about we choose Uranus? How about Neptune? Okay, now I'm going to look down here, and it tells me that, now look at that. Wow, look how slow Neptune is going. This is still moving, by the way. This is just how slow it is compared to, remember how fast Mercury was going? This is the same scale. Mercury's like zipping around, but Neptune's just going insanely slow. Okay, in fact, it tells us here how long Neptune takes. So we're going to kind of flip this equation around and do one more problem using Kepler's laws here. So for Neptune, the period is 165 years. That's one orbit, takes that long. So the question then could be rearranged to say, well, now what must its semi-major axis be? How many astronomical units would that need to be? So we're using the same equation, right? P squared equals a cubed, but now the trick is we need to solve for a instead. So now how do you get that a by itself? Well, you have to do what's called a cube root. And maybe you haven't had ever a reason to do a cube root before, but there are a couple ways to type it into your calculator. So the way you write a cube root is just like a square root, but you put a little 3 right there. And you'd have to do that to both sides, right? That's our little algebra. We do the same thing. So again, if you wanted to write this right on your equation sheet, you could. But if you ever needed to solve for just the semi-major axis, you need to take the cube root of the period squared. Now, there's a couple ways that you could type that into your calculator. I'll show you some example problems later on, some more example problems. But in general, the cube root, you might see that you have a cube root button on your calculator, but you can always do like use it like raised to the power of another. I'll show you. Okay, so let's just do this example though. So I have that the semi-major axis will equal the cube root of 165 squared. All right. Now, one way you could type that into your calculator, so 165 squared is going to be like this huge number, 27,225. So if I'm typing that in my calculator, I'd probably type it like this, 27,225. And I would write it to the power of 1/3. Now, cube root is the same as raising something to the power of 1/3. So to do that, to raise it to the power of 1/3, you might want to actually type in your calculator like caret parentheses 1/3. That means like raise it to the power of, and you put it in parentheses 1/3. You might also, in your calculator, it might not be a caret, it might be like X to the Y button, right? You might have like a button like that. And then you would type that and then 1/3. Okay, and that's how you would end up taking the cube root. In this particular case, let's see. I'm going to do this, 27,225 to the power of 1/3. And I end up with about 30. 30.08, so 30.1 AU. So you can see I just solved that. Again, if you were watching, playing along at home, you'd probably see that right down there, 30.1. So look at all that crazy math on here. But the point is that this equation is something we can use to relate the time it takes a planet to go all the way around and its semi-major axis, or that more or less like average distance from the planet to the star. Okay, I hope that helps as you're thinking about Kepler's 3 laws.